Hello, today I'd like to share some work with you that has been recently published in Gyres. Myself and my colleagues have been investigating the vorticity budget of ocean gyres on the sea grid, and in doing so, we've identified numerous spurious forces that not only exist in that budget, but can in fact dominate that budget. So before we get to the results, it's probably best to refresh on what we mean by a vorticity budget. Well, the vorticity budget emerges from something called the depth integrated vorticity equation. And what this essentially describes is how forces generate rotation in the ocean. So each contribution in this equation arises from force, and it just describes how that force can generate vorticity or local rotation, if you prefer. So each term in this equation arises from an original acceleration. So the first term here on the right-hand side originates from Coriolis acceleration. Second arises from pressure gradients at the sea floor. Wind stress curl arises from wind stress, and bottom stress and advection and diffusion. To be really precise about how the vorticity term and the acceleration are related, let's zoom in on that Coriolis contribution that we're going to look at quite a bit in this presentation. So we see that to get the Coriolis vorticity term in that equation, we need to take the original acceleration, Coriolis acceleration, integrate it over that, and then take the curl. So what this exactly describes is the rotational effect of the depth integrated acceleration. Now, this method has been presented in a sort of analytic way, but we can also apply this to accelerations in models. But rather than using a smooth continuous acceleration, we're going to be using a discrete acceleration, which are the momentum diagnostics. Now, we use this analysis in a couple of systems, but we're going to talk about specifically the results from the Weddell Gyre today. And this is a model, this is from the quarter degree global model. It has realistic forcing, realistic bathymetry. And because of that, when you look at the grid point values of these diagnostics, they're very, very noisy and very difficult to inspect by eye. So what we do is choose an area to integrate over. Now, we chose to integrate over the area enclosed by numerous streamlines of the Weddell Gyre. And this has a huge advantage because depending on the value of the streamline you're looking at, you can either get a full budget of the gyre. So if you go for a streamline that is right on the outer edge of the circulation, you will basically have a full vorticity budget of the gyre, or you could choose an interior streamline, and that will tell you more about what's going on in that sort of core circulation, right down at the center. So that's this sort of size 55 value here. So what we did was we just sampled a whole bunch of streamlines and did a whole bunch of integrations to get a full profile of the gyre. And when you do that, you get a plot that looks like this. Now, this might not be familiar to many people, so we're going to talk about how to look at this plot and how to get the most from it. So first of all, this x-axis is the value of streamline we're integrating inside of. As I was saying, the lower values of psi envelop almost the entire gyre. So the lower values of psi give a sort of full budget of the gyre, and the higher values of psi only look at the deep sort of interior of the circulation. We've made sure that positive contributions to the plot contribute to spinning the gyre up. So these are diagnostics that are vorticity terms that are generating rotation that complements the gyre circulation. So it's in the same direction. And that can be interpreted as sort of spinning the gyre up. The negative values of the converse, they're generating rotation in opposition to the gyre circulation, and therefore is trying to spin it down. So these are acting more like a drag. And finally, this sort of sharp discontinuity here, I just want to add that that is not something physical. That is due to us essentially running out of contours to find. For this analysis to work, the contours have to be sufficiently closed. Otherwise, you start getting a lot of problems. Okay, so let's actually look at the physics of what's going on here. So we note that the dominant positive term is this blue contribution here, right? And this arises from the curl of the wind stress. So this is suggesting that wind stress is the primary mechanism for spinning that gyre up. So we could reasonably conclude that this is a wind-driven gyre. We note that this purple contribution here, which is negative, is from bottom pressure torque. So this suggests that pressure gradients at the sea floor are doing a good amount of work in slowing that gyre down, trying to regulate its circulation. But the most striking result I want to talk about today is this orange contribution, which is the dominant negative contribution. And this arises from the curl of the Coriolis acceleration. Now, this is unusual because it is the dominant opposing force but in this budget, but if we do the pen and paper calculations, so if we look at the analytic vorticity budget, we see that this should actually integrate to 0 as a consequence of the divergence theorem. So this is a case where the analytic budget does not agree with the model's discrete budget. So why is that the case? The answer is that orange contribution contains numerous spurious components. So let's zoom in on that orange contribution now. Now, in our paper, we decompose this orange contribution into 5 spurious components, and it's all about the structure of how we calculate the Coriolis acceleration. But in this example, only 2 particularly matter. The first is the contribution due to partial cells, that purple line there. This arises from the cell thicknesses at the seafloor varying horizontally. This is a sort of crude way to represent a smoother bathymetry. The second contribution is from model level steps. This is an inevitability in Z-coordinate models that eventually the number of model level steps have to change, and as a result, you get a sort of staircase-like bathymetry. Now, if we look at the grid point values of these model level steps, you can see that it's not a very realistic force. You can see that you have these sort of bands of contribution that are localized to those points where the number of model level steps change, at those sort of steps in the bathymetry. And this obviously isn't something that happens in the real ocean. So we can see that it's quite a non-realistic force, and it is dominating that orange contribution. So in conclusion, we've shown that spurious topographic forces can emerge from the discrete Coriolis acceleration, and they can dominate the vorticity budget of that circulation. The identified forces emerge when we use a C grid with Z coordinates. In our paper, we conclude that terrain following coordinates will alleviate that signal, or using an alternative horizontal discretization. So changing your grid from a C grid to a B grid would alleviate this contribution as well. Once again, as I've said, this paper has just been recently published. So if you're interested, take a look. And thank you very much for listening.